Have you ever looked at two incredibly complex systems and just had a gut feeling they were the same deep down? Maybe it's two different pieces of software, each defined by this massive, messy matrix of data. How do you prove they're functionally identical when all the numbers look completely different? You need a fingerprint, a non-negotiable one. And that search for a unique, simplifying structure is what we're diving into today. The Frobenius normal form. It's also known as the rational canonical form, or RCF. Okay, let's unpack this.
It's a fantastic topic, and its mission really is to solve what we call the matrix similarity problem for good.
Similarity just meaning one matrix is a different view of the other, like a change of perspective.
Exactly, change of basis. And the RCF is the single unique form you can get to through that change. So matrix B is similar to matrix A if and only if they have the exact same RCF. It's definitive.
I see. And you emphasize the word rational. Why is that part so important?
That's the key to its power. It's rational because you can find this form without operations that change when you extend the field you're working in.
So we're not just talking real or complex numbers.
Not at all. This works for matrices over finite fields, the kind used in cryptography. It shows that similarity is baked into the matrix right from the start in its home field.
Okay, but that immediately brings up a question for me. Why do we need this? We have diagonalization, we have the Jordan normal form. Aren't those powerful enough?
That's where the RCF really shines. See, those traditional methods, they depend on finding eigenvalues.
Which means factoring the characteristic polynomial.
Right. And what if you can't? What if your matrix is over the real numbers, but to factor the polynomial, you have to jump into the complex plane? The Jordan form only exists if you allow that. The FNC just bypasses that whole problem.
So we stay within our original set of numbers. But there has to be a trade-off, right? If we're not getting a simple diagonal matrix, we must be settling for something more complex.
That's exactly right. The trade-off is that we accept something called the companion matrix. The FNC works by breaking the space down into these stable subspaces. We call them cyclic subspaces. The action of the matrix on these subspaces is then described by that companion matrix. It's the simplest block form you can get that represents the action of the minimal polynomial on that little subspace.
So it's the best structure we can get without, leaving home.
Precisely. And that's what makes it different from, say, the primary rational canonical form. The primary form does reflect factorization into irreducible parts over your field.
So it's a halfway house in a way.
You could say that, and when those factors are linear, the primary RCF actually becomes the standard Jordan form. But the FNC, by avoiding factorization entirely, is just universal.
Okay, here's where it gets really interesting for me. The uniqueness. How do we make sure that this decomposition, this block structure, is the only one possible?
That is enforced very rigidly by what we call the invariant factors.
Invariant factor.
Right. A decomposition into those cyclic subspaces always exists, but to make it unique, we add a rule, a strict divisibility condition. The polynomials associated with each block have to divide the next one. So F1 must divide F2, which divides F3, and so on. Think of it like a set of nested matryoshka dolls.
That divisibility chain, that's the lock that guarantees the unique structure. This ability to take a complex structure and assign it a unique, predictable identifier, that's so fundamental. That search for universal structures like the FNC provides is exactly what drives so much of modern AI and automation. And speaking of structured solutions, if you're looking to uncover where intelligent agents can make the most impact for your business or personal life, or maybe you need help with AI training, automation, or software development, check out Embersilk. You can visit embersilk.com for your AI needs.
And what's so elegant is that the final RCF, that block diagonal matrix, is built from the companion matrices of those unique invariant factors. And the biggest one, the last one in that chain, F sub, always turns out to be the minimal polynomial of the entire original matrix. It's the signature of the whole transformation.
So at the end of the day, what does this all mean for us? The Frobenius normal form gives us this elegant, unique fingerprint for any square matrix. It proves whether two complex systems are fundamentally the same without ever needing to chase down messy, complex eigenvalues. It's a real triumph of abstract algebra, confirming that under all that complexity, there's a rational, predictable structure just waiting to be found.
Indeed. And just think about that for a second. The ability to define a single, unique, stable form like this for any matrix over any field, it suggests a kind of profound universal structure that underlies all these complex transformations. It's really a testament to the unifying power of mathematical theory.
If you enjoyed this deep dive, please subscribe to the show.
Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.